Hi, my name is Vivek Kumar, and my topic for the seminar is Babel Routing Protocol. I have taken the same topic so that I can explain more about Babel Routing Protocol. So let me refresh what I have explained in part 1 of the video. So Babel routing protocol is a loop avoiding distance vector routing protocol. This is very important here. It's a loop avoiding distance vector routing protocol that is designed to be robust and efficient on both wireless mesh network as well as wired network. So also we need to keep three things in mind that it is based on Bellman-Ford algorithm, which I have explained in detail in part 1, and and it does guarantee loop freedom by using feasibility condition. And the third is it can carry routes for both for multiple network layer protocol like IPv4 and also as well as IPv6. So there is a problem arises in Bellman-Ford algo named transient loop. So if connection between two node fails, then feasibility condition is introduced to solve this transient loop problem. But by adding feasibility condition, we also add more constraint on how feasible routes is discovered, which leads to starvation of nodes in network topology. That means even though there is route from source to node A, the node A will not reroute its path. So to solve this problem, I have explained how every route carries a sequence number so that nodes should not suffer any kind of starvation. One more important point we need to keep in mind that sequence numbers are used for determining feasibility. They are not used in route selection. So this is a very common misconception, and we need to keep in mind. I'm repeating it again. Sequence numbers are used for determining feasibility condition. They are not used in route selection. like like a node ignores the sequence number when selecting the best route for a given destination. Let's take an example to explain this properly. In this diagram, say the link between S and A fails and A is suffering from temporary starvation. Then A must wait until S generate a new sequence number and the network propagates it. In Babel, temporary starvation is explicitly signaled by node A, which is not the case in DSDV. In DSDV, the sequence number of a source is increased periodically. A route becomes feasible again after source increases its sequence number and the new sequence number is propagated through the network, which may require a significant amount of time. Whereas Babel takes a different approach. When a node detect that it is suffering from a potential starvation, it sends an explicit request to the source for a new sequence number. This request is forwarded hop by hop to the source, and upon receiving that kind of request, the source increases its sequence number and broadcasts an update which is forwarded to the requesting node. It is important to note that after a change in network topology, all not all such not all such requests will in general reach the source, as the sum will send over the links that are now broken. So there may be some broken links which was supposed to through which the request were supposed to go, but it's broken now. However, if the network is still connected, then at least one among the node suffering from starvation has a route to the source, and at least one such request will definitely reach the source. Since requests are forwarded with no regard to the feasibility condition, they may in general be caught in a forwarding loop. So this is avoided by having nodes perform duplicate detection for the request that they forward. The discussion so far assumes that each prefix is originated by a single router, but in real networks, it is often necessary to have a single prefix originated by multiple routers. For example, the default route will be originated by all the edge routers of a routing domain. In general, we want it to be possible to have multiple nodes that announces the same prefix without synchronizing sequence numbers. Since synchronizing sequence number between distinct routers is problematic, Weber treats roots for the same prefix as distinct entities when they are originated by different routers. So every root announcement carries the router ID of its originating router and the feasibility distances that are not maintained per prefix but per source, where source is a pair of router ID and a prefix. Babel guarantees loop freedom for the forwarding graph to every source. Since the union of multiple acyclic graphs is not in general acyclic, but Babel does not in general guarantee loop freedom when a prefix is originated by multiple routers. But it does guarantee that a loop disappears in O of n time complexity, where n is the size of loop. Consider for the example the following topology where A has selected the default route through S and B has selected the one through S dash. Now suppose that both default routes fail at the same time, right? Then nothing prevents A from switching to B, right? And B simultaneously switching to A. So, as soon as A had successfully advertised the new route to B, the route through A will become unfeasible for B. And similarly, as soon as B will have advertised the route through A, the route through B become unfeasible for A. So the routing loop disappears at latest when routing information has gone around the loop. Since this process can be delayed by lost packets, Babel makes certain efforts to ensure that updates are sent reliably after a router ID changes. After the router after the routers have advertised the two routes, both source will be in their source table, which will prevent them from ever participated in a routing loop involving routes from S and S, and this is how the loop will disappear from this topology. So far we have seen how Babel deals with loop in network topology. Now I will explain how messages and acknowledgements are transmitted in the network. Every Babel speaker is assigned a router ID, which is an arbitrary string of 8 octets that is assumed unique across the routing domain. Babel protocol packets are sent in body of a UDP datagram, and each Babel packet consists of a 0 or more TLVs, and most TLVs may contain sub TLVs. So the source address of a Babel packet is always a unicast address, and Babel packets may be sent to a well-known multicast address or to a unicast address. In normal operation, a Babel speaker sends both multicast and unicast packets to its neighbors. With the exception of acknowledgements, all Babel TLBs can be sent to either unicast or multicast addresses, and their semantics do not depend on whether the destination is a unicast or a multicast. A Babel speaker does not need to determine the destination address of a packet that it receives in order to interpret it. And these are the slides I have added to have an overview what kind of tables is maintained and different parameters in order for the message transmission in the network. Like here the neighbor table is there, and these are the different entries and data it contains, like the local nodes interface over which neighbors is reachable, and the address of neighboring interface, and the history of recently received multicast hello and unicast hello packets from their neighbors, and similarly these different entries. And in source table three entries is there, like the prefix, the router ID of a router originating this prefix, and a pair like named sequence and matrix. And then similarly in router table, these are different entries, like the source for which the route is advertised, the neighbor that advertised this route, and the matrix and the sequence number, and the next hop address of this route. Similarly, also a boolean flag is maintained. When it comes to acknowledgement, a Babel speaker may request that a neighbor receiving a given packet rely with explicit acknowledgement within a given time. Well, the use of acknowledgement request is totally optional, but every Babel speaker must be able to rely to such a request. The Babel must be able to reply if acknowledgement request is there. And the important point here is that an acknowledgement must be sent to a unicast destination. On the other hand, acknowledgement request may be sent to either unicast or multicast destinations, in which case they request an acknowledgement from all of the receiving nodes. So this is a very important point. When to request acknowledgement is a matter of local policy. The simplest strategy to never request acknowledgements, right, and to rely on periodic updates to ensure that any reachable routes are eventually propagated throughout the routing domain. In order to improve convergence speed and to reduce the amount of controlled traffic, the acknowledgement request may be used in order to reliably send urgent updates and retractions, especially when the number of neighbors on a given interface is small. Since Babel is designed to deal gracefully with packet lost on unreliable medium, sending all packet with acknowledgement request is not necessary and totally not recommended, as the acknowledgement causes additional traffic and may force additional address resolution protocol. Now the topic is matrix computation. So in matrix computation, a root's matrix is computed from the metric advertised by the neighbor and the neighbor link cost. Just like cost computation, matrix computation is considered a local policy matter. As far as Babel is concerned, the function m used for computing a matrix from a locally computed link cost c and a matrix m which is advertised by a neighbor, and this must satisfy the following condition. The first one is the matrix must be strictly monotonic. If c is infinite, then the m function is also infinite. If m is strictly monotonic, then the function should be always greater than m. The second condition is that the matrix should a matrix should be isotonic, and for that, if m is less than new m dash, then the function for m should be less than the function m for m dash. Okay, and the function c comma m is equal to c jar m. While strict monotonicity is essential to the integrity of the network, it is enough to guarantee that the Babel will converge to a loop-free Nash equilibrium, whereas isotonicity ensures that this equilibrium is the tree of shortest path, and Babel will still converge to a loop-free configuration. So now, for the topic root acquisition, when a Babel node receives an update from its neighbor, then it checks whether it already has a root table entry indexed by like prefix p lane and neighbor. If no such entry exists, and in that case, if the update is unfeasible, then it may be ignored. If the matrix is infinite, then update is ignored. Otherwise, a new entry is created in the root table and it's updated. And second case, if such entry exists, so in that case, if the entry is currently selected, then the update is unfeasible and the router id of the update is equal to the router id of the entry, then the update may be ignored. Otherwise, the entry sequence number, the advertised matrix and router id are updated. Let's see the security in Babel. So Babel is a completely insecure protocol. Without additionally securing mechanism, Babel trusts any information it receives in plain text UDP datagrams and acts on it, whatever the data has been received by UDP. So now there is a possibility that an attacker that is present on the local network can impact Babel operation in different ways. Like it can create a spoof, it can spoof a Babel packet and redirect traffic by announcing a route with smaller metrics and a larger sequence number, or a longer prefix. Similarly, it can spoof a malformed packet, which can cause an insufficiently robust implementation to the crash. So finally, to conclude, Babel is a robust and flexible routing protocol. It is reasonable on wired network and also reasonable on wireless meshes. It's a great framework for experimenting with new ideas like source specific routing, radio interference sensitive metrics, and delay based routing. More information can be seen in the document of the Babel routing protocol. And thank you.